Hi guys, and welcome back to my channel. Today I'm going to be doing a COMSOL tutorial on stresses in a pulley. I'm using COMSOL version 6.0 and this will only use the multiphysics package. So here's some background information on the model. This example contains a study of the stress distribution in a driving pulley. The analysis shows the stresses as functions of the pulley's angular velocity. Okay, so F1 is load side, F2 is slack side of the belt. The relationship between these forces is given by the Capstan Equation, or Eitelfein's formula as it's referred to in the German literature. F1 over F2, so load side over slack side forces equals E to the mu beta. Mu is the coefficient of friction and beta is the contact angle between the belt and the pulley. So we've got beta is shown here, mu is just a coefficient, and then we've got omega here and theta here. So beta is 170 degrees, the contact angle between the belt and pulley. And this equation is valid if a condition of impending slippage between the belt and pulley prevails. It's also necessary to state that the peripheral force, the force that transmits the power, is F sub U equals F1 minus F2, load side minus slack side, equals M over R. So M is the applied torque and R is the outer radius of the pulley. Okay. It's then possible to define F2 as F sub U over E to the power of mu beta minus 1. So substitute the force in the slack side of the belt. You can derive the loads on the boundary of the pulley. In mechanics and the theory for flexible wires, the following equilibrium equations appear. F sub n equals S over R, where S is the tension force and R is the radius. And F sub t equals mu times F sub n, where F sub n is the normal component directed inward, and F sub t is the tangential component directed against the rotation. If you apply these equations, the loads on the boundary of the pulley become F sub n of theta as a function of theta equals F2 over R times E to the power of mu theta. And F sub t is a function of theta equals mu, and again theta from this diagram is a rotation about the axis of symmetry here. F sub n of theta equals F2 over R times E. Already said that one. S sub t of theta equals mu times Fn of theta. Alright, inertial loads are generated due to the rotation of the pulley and calculated as F sub R equals R times omega squared times rho. R is the radius, omega is the rotation speed, and rho is the density. The pulley is fixed at its inner diameter and the inertial loads are active in the entire geometry. A parametric analysis shows how the rotational speed affects the stress distribution in the pulley. Because the power of the pulley shaft remains constant, the torque, defined as the ratio of power by the rotational speed, decreases with increased speed. This means with increased rotational speed, the inertial load increases while the driving belt force decreases. The following plots show the von Mises stress distribution inside the pulley for different rotational speeds in RPM. As evidence from the plot, the stress distribution changes as the rotational speed increases. Okay, so we're going to generate these plots and we can talk about that at the end. And then we'll also do a plot of von Mises stress versus rotational speed. Okay, here's a little more detailed view of von Mises stress in a part of the pulley evaluated during accurate derivative recovery. The stress field was evaluated Okay, so this is just making it smoother if you want a more detailed look with more resolution. And in this example, dynamic effects have been ignored. In reality, it is possible that vibrations in the pulley could occur if the rotational speed coincides with natural frequencies of the pulley. So we're going to do a new model, Model Wizard, and this will be a 2D model. We're going to expand structural mechanics and choose solid mechanics, solid in parentheses. Choose add, study. There's only one physics module for this study, and then we're going to do a stationary study today. And then jumping into geometry, we'll be importing the geometry. So I already downloaded that file ahead of time, so you can download that at the link in the description of this video if you have COMSOL. Okay. And import. So there's the geometry. And now to set the global definitions. So we're going to click parameters 1 under global definitions. Oh, I should save this. I always get so far into it before I save. So let's call this stresses in pulley. Okay, and I also already saved the text files for the parameters and variables beforehand, so we'll just import load from file rather, and find the text file. I saved stresses and pulley parameters.txt. And then for variables, we're going to click on home toolbar, and under the FX icon from this drop down we'll choose from the A equals icon for variables, we're going to choose global variables. Again, load from file and find the stresses and pulley variables text file. There's our variables for radius, theta, peripheral force, F sub mu, F2 is the belt force on the slack side, F sub n is the normal force, F sub t is the tangential force. Okay, on to materials. So we're going to make this pulley component aluminum. Add material from home toolbar. So up here, this honeycomb looking icon is the materials, add material, and then we will search for the built-in. So we can expand built-in and just find aluminum, or you can type it in. There's actually a few different ones here. So we have aluminum 3003 something, aluminum 6063, but we just want this one. So by double clicking or adding the component, you'll see aluminum appear under here in the model builder drop down under materials. So I'm going to X out of that window, and now we will make our definitions. So in the definitions toolbar up here right next to home, click coordinate systems and choose cylindrical system. So we're changing from an XYZ orthogonal coordinate system to here we go, the XYZ icon in the middle of the toolbar, cylindrical. Changing to a radius theta psi based coordinate system. Alright, now we're ready to build the physics boundaries. So under solids, we will click on solid mechanics, and in the settings window for solid mechanics, locate the 2D approximation window or section. So about halfway down here from the list, we're going to choose plane stress. Locate the thickness section and in the D text field, type D. So we're saying instead of the default value of 1, we're going to reference the global definition for variable D. Body load. In the physics toolbar, click domains. So I'm clicking on physics up here, domains, and choosing body load. Let's see, where is that? Here we go, under volume forces, the first one. And then we have a new selection under the physics module drop down. Select domain 1 only. So that's the only domain. Well, I guess technically you have all the negative space domains. In the settings window for body load, locate the coordinate system section. And it looks like we're going to change this from global coordinate system to cylindrical system, system 2. Locate the force section and specify the FV vector as x component r times omega squared times solid dot rho. How would you know to use this expression with that syntax? Let's see. So rho comes from the material. Right here, density is RHO, rho. And I'm just struggling to see, how would you know? I guess because the material is solid, that's why it's solid dot rho. And I'm sure that documentation is available somewhere. I'm just not exactly sure where you would find it if you didn't know to enter this exactly. So obviously R, you're just, you're calling the value assigned to these variables that you defined earlier. R and omega squared, those are pretty straightforward. But I'm not sure why this isn't just rho. Why a solid dot rho? Maybe it's because R and omega are both under, well, R is under variables, omega is under parameters. So honestly, I don't know. I guess you would just figure this out. Like, let's try just putting in rho and see if it turns yellow. Yeah, see, it doesn't recognize it. So I guess that's what would prompt you to go digging for documentation, because it can find variable R, it can find parameter omega, but it can't find a global definition for rho. So I am guessing that by telling it solid.rho, this says, okay, you're looking for an attribute of solid, so go look in the material, which is a solid. So sometimes I'm learning as I'm doing these. Not sometimes, all the time. So we're learning together here. Alright, so that's our expression for the x component of force per unit volume, and the y component is just going to stay at 0. And now, r, not x and y, r and phi, because we switched coordinate systems here. And now we're moving on to predescribed displacement. In the physics toolbar, click boundaries, choose predescribe displacement 1, select boundaries 57, 58, 62, and 63. So we're going to click in the graphics window anywhere in here. Do Control A to select all. So all of our boundaries are selected now in the boundary selection of the settings window. And now I can just choose everything but these boundaries I want to select. So up to 63, subtract. I want 63, 62, and then I'll subtract from 61 to 59. I'm just doing a shift button there to control all and list, and then 58 and 57 I want selected. So 56 through 1, 56 shift 1, then the minus button. Now we've got the center of this pulley. Okay, so there's other ways you could figure this out. Obviously, you could just hover and find them, but that's one approach. So we have a prescribed displacement in the center of the pulley. In the settings window, locate prescribed displacement section, and in the X direction, we want to click the box for the X direction and the Y direction. Boundary load 1. In the physics toolbar, click boundaries and choose boundary load. Select boundaries 67 and 68 only. Okay, so let's see, we got a #67 and 68. And we're going to specify the FA, force per unit area vector, as negative F sub n for the R component and F sub t, the tangential force, for the phi component. So what this is saying is the normal force, negative F of n, since it's going downward, is a function of R, and the tangential force F sub t is a function of phi. Alright, now we're ready for the mesh. In the model builder window, under component 1, click mesh 1. And in the settings, we're going to go to physics controlled mesh and change from normal to fine. So one element size finer than normal. Alright, and build all. The mesh should contain about 2,600 elements. Case study 1. We're going to do a parametric sweep for specified values of n, or revolutions per minute. Okay, so we're going to go to study toolbar, parametric sweep, the 1, 2, 3 column icon, locate study sections and add this plus icon at the bottom of the table. And the default value will be the first value from the drop-down menu, which is mu, and we're going to change this to n revolutions per minute. Then we'll fill in the range of values we want to sweep through. So you type in range, open parentheses, first value, second value, third value, and depending on your study selections, it will hit only each of those 3 values, or you can sweep between those values with more resolution. Since the stress concentrations depend on the RPM, mesh adaptation must be run separately for each case. Therefore, disable the parametric solver. Click to expand the advanced settings section at the bottom, and from the use parametric solver list, choose off. Alright, so we're ready for stationary study, step 1. So we're going to click on step 1, stationary, and in the settings window, choose adaptation. Under the adaptation and error estimates section, which you have to expand here, we're going to choose choose adaptation and error estimates, changing from the default of none, and then from the error estimate list, choose functional. So defaulted value is L2 norm of error squared, but we are changing it to functional, and for the functional type, instead of predefined, we'll do manual. In the functional text field, type comp1 dot solid dot w sub s total. Paste the value from the tutorial and keep moving. Find the mesh adaptation subsection. Mesh adaptation subsection. Where is that? And from the adaptation method list, choose rebuild mesh. Alright, and the element count growth factor text field, type 1.3. Okay, so I don't see any field with this name, element count growth factor, but just based on the context and assuming this is some difference between an older version and the current version 6.0, I'm going to guess the maximum coarsening factor is the element count growth factor. So we'll see if that works. Change the adaptive mesh refinement solver settings to use an error estimate, which is more sensitive to stress concentrations. The total elastic energy has this property since it is in fact quadratic in the local stress. As the critical stress concentration regions are small, select mesh initialization as refinement method since it can refine more aggressively in small areas. Or in the study toolbar, click show default solver, which is this flag icon, and in the model builder window we'll expand this node that pops up, solver configurations, and then expand solution 1 and click on stationary solver 1 node. Right click study 1 solver configurations. We're going to right click on the adaptive mesh refinement underneath that stationary solver 1, and from this menu, why am I not seeing compute? Okay, so right click doesn't work, but if you click on adaptive mesh refinement, you can just click on compute from the settings settings section. Takes a few seconds to compute. And then we'll look at results. First of all, the von Mises stresses and a boundary loads. Well, we've got a volume load solid plot and a boundary load solid plot. Alright, so in the home toolbar, click add plot group, going back to home, add plot group on the right, and we're going to add a 2D plot group. So now we have 2D plot group 4 that appears down here under results in the model builder window. In the settings window for 2D plot group, type von Mises in the label text field. Use a filled contour plot to clearly see where different stress levels occur. For that purpose, add a contour plot and define its settings to display the von Mises stress variation. So that's what we're doing. Locate the data section and choose study 1, parametrics solutions, solution 3. Why is that not appearing? Oh, I guess I never ran it. Maybe I missed that step. So I'm just gonna hit run under parametric sweep. Alright, there we go. So we're going to choose the parametric solutions from the drop-down menu as our source data set. And, alright, and then we're going to add a contour plot. So right-click von Mises and choose contour. And in the settings window for contour, click replace expression, the red-green caret arrow or icon up here. And from the menu, choose component 1, solid mechanics, stress, solid.Mises, von Mises stress, and newtons per meter squared. Double click. And you see the expression is populated by our new expression, solid.Mises. Alright, locate the expression section, and from the unit list, same section, I don't know why they said that, choose megapascals. Okay, megapascals is our unit of choice here, and then locate the levels section a little further down, and then the total levels we will overwrite 20 and write 10. And then for coloring and style, we'll choose filled instead of line, and plot. Oh, beautiful. Alright, so we've got our von Mises stress in megapascals with dark blue representing the high, or the low end, of 4 megapascals, and red representing the high at 68 megapascals. So you can see that around the edges there's low stress. Okay, so there you go. This is with the refinement, or with the smoothing selection. And now we're going to make a line plot of the von Mises stress at a specific point as a function of the rotational speed using cut point 2D. So in the results toolbar at the top, click cut point 2D, box with a dot in it, and locate the data section. So we're going to choose solution 3. Well, since I did it out of order, I have parametric solutions as solution 6 for me. Locate the point data section, and for X, we're going to put in 0.019 meters, and the Y value, Y coordinate, will be 0.054 meters. So let's see, at about 0.02 and 0.054. Right here. Alright, and then in the results toolbar, click 1D plot, the squiggly line icon. And in the settings window, we're going to label it von Mises versus rotational speed. Okay, and in the data section, we're going to choose the cut point 2D1 that we just added. And finally, from the parameter selection refinement level, choose last. So you can choose first, last, from list, or manual. So we want the last value at the let's see what from list. Oh, there's only 3 values you could choose from, 0, 1, or 2. So last is level 2 refinement. And now for the point graph, we'll right click von Mises versus rotational speed and choose point graph. So we're choosing what kind of graph we want to make using this data where we just specified to source. Click replace expression in the y-axis data section, and then we're going to expand component 1, expand solid mechanics, expand stress, and choose solid.Mises von Mises stress, and then change our unit once again to megapascal. Alright, and locate the X data section. So that was for y-axis at the top. X status, we're going to change axis source data to N. Alright, in the model builder window, click von Mises versus rotational speed. In the settings window for 1D plot group, locate the plot settings. Select the X-axis label checkbox. Check. And in the associated text field, type rotational speed and RPM. Click to expand the title section. In the title area, type von Mises versus, or von Mises stress at x equals 19 millimeters, y equals 54 millimeters. oh, we've got to change to manual first, and then that appears. So our title of the graph is going to be von Mises stress at these coordinates. Alright, notice that by selecting different solution set entries on the dataset list and the setting window for the 1D and 2D plot groups, you can visualize different results at different mesh refinements. Okay, and then we'll hit plot in the 1D plot group. So there you go. You have a V shape resulting here with the lowest von Mises stress occurring at about, what is this, like 5,500 RPMs, and then shooting up towards 9,000 RPMs on this side, and then also very high stress at low RPMs on the 0 to 5,000 RPM range. If you hit zoom extents, you can see the whole graphics, the entire graphic. Finally, zoom in on the center of the pulley to get a close-up view of the stress distribution. In particular, notice that the accurate derivative recovery method gives a smoother and more accurate solution. So this is just saying you can go to your graphics window and zoom extents, you can see the whole thing, and if you do zoom in, you can either hit this button or you can use the control at the same time as the wheel on your mouse, and it gives a more accurate solution than without the refinement. So this is refinement level 2. Okay, so going back to where they discuss the results here, I said, as evident from the plots, the stress distribution changes as the rotational speed increases. Okay. And at the point we chose for our point graph 1, von Mises stress versus rotational speed, the von Mises stress is maximal for the reverse rotational speed at n equals 1,000 RPM. The plot in figure 5 shows how the rotational speed affects the von Mises stress at this specific point. First, the stress decreases, but then the effect of the inertial loads becomes dominating and the stress begins to increase. Okay, so we have competing effects here that are balanced or optimized best at this RPM between about 5,000 and 6,000. So on this side of it, the stress is caused by the effect of inertial loads dominating, and on this side of it, let's see, what are our competing? Okay, because the power at the pulley shaft remains constant, the torque, defined as the ratio of power by rotational speed, decreases with increased speed. So on this side of it, you've got decreased torque, meaning the rotational speed is greater than the power that remains constant in the numerator. But here you've got very high torque. Rotational speed is low, and the denominator of the same constant power in the center of the pulley. Okay, so inertia dominates over here, and the power from the center of the pulley dominates over here. Or I guess torque dominates over here. You know what? like I said, structural mechanics is not my forte, so I really like doing the animations. It just kind of helps me visualize what's happening with time. So let's do zoom extents. Let's add an animation real quick. So let's go to results, animation, player, and subject, we're going to choose von Mises. Okay, and the scaling changes between the low end and the high end. So if you iterate or loop over everything, including n equals 1000, you're going to end up with high values of like 111 up here. So it makes it harder to actually see what's going on. So if you just choose the last half from like 5500 through 9000 RPMs, let's see what that looks like. That way your scaling stays at a high value of about 65 megapascal stress. So it's not exactly the same as this, but you can actually get a better sense for how the stress is increasing. The von Mises stress is increasing with an increase in RPM. So I'll play that again. It starts out very low all over the pulley, and then you gradually start to see an increase as you go from 7500, 8500 to 9000 RPMs, which again reiterates what we see here, going from about 5500 up to 9000. There's a linear increase in von Mises stress at this cut point here at x equals 19 millimeters, y equals 54 millimeters. Let's see, so that would be right about here where that cut point graph is looking at. Alright, so that was the tutorial for today, and if you enjoyed this one, please like, comment, and subscribe, and I'll see you in the next video.